Okay, I'll go ahead and introduce our next two presenters, who are both from Linaro. This is Leif Lindholm. He is one of the stewards for the open source Tiana Core project and maintainer of the ARM components. And Ard will be showing up momentarily.
Yep. Fortunately, the first half of the talk is mine anyway, so I'll go with that. Right, so the title of this is How Writing Portable UEFI Drivers Improves Reliability and Helps Me. And if you attended the last UEFI Plugfest in Taipei, you might find this extremely familiar because it presented exactly the same talk there, although I think one slide's been slightly tweaked. Let's jump right into, so architectures versus platforms. What's in an architecture? Porting a device driver to another architecture isn't just a question of a different instruction set, a different tool chain. UEFI defines fully portable interfaces that lets you write device drivers that will run anywhere, but x86 lets you get away with shortcuts that you cannot rely on ARM systems specifically and potentially other architectures as well. And secondly, when people talk about x86, they generally mean a descendant of the IBM PC compatible platform. On the ARM side, we don't really have that history, neither on the 32-bit ARM or the 64-bit AR64 side do we have such a rigidly defined platform anywhere. So as an example, we can talk about the memory organization in ARM platforms. The ARM architecture does not standardize the CPU's view of the physical address space in any way. So looking at the on top, it's the your typical PC memory map. Your DRAM starts at 0, and then you have some I/O stuff and some reserve stuff, and then if you have more than 4 gigs of RAM, then you can have more DRAM above that. On ARM systems, even standard peripherals, like the generic interrupt controller, does not have a defined location in the address space. It could be placed anywhere. The bottom half shows 2 completely valid memory map layouts for ARM systems. So you could have only MMIO below 4 gigabytes, you could have only DRAM before 4 gigabytes, or any kind of combination in between at all. One of the things that's been kind of tedious for us moving across and trying to get more stuff compatible with the ARM architecture has been stuff that tends to still work on PC, such as randomly trawling through address space for ACPI or SMB BIOS tables, looking for magic numbers, which, as you see, in the first ARM example, well, that probably won't kill you. In the second ARM example, well, that's probably going to kill you. But in general, in Linux, devmem should not be enabled in a production system for ARM. There's also no need for it. So, about UEFI on ARM. The bindings for AR64, the 64-bit ARM architecture, were first included in UEFI 2.4, released in June 2013, with the initial support merged in upstream EDK2 on the 18th of July. So basically 3 weeks later. In UEFI, 32-bit ARM is known as uppercase ARM, even though the company has now decided to use different case. And 64-bit ARM is known as AR64. For practical purposes, no processor older than ARM architecture v7 can really implement support for UEFI. For data centers and laptops and things, we only really care about AR64 these days. ARM. So as I mentioned, there's vast array of different ARM systems out there. So ARM's partners license processors or the architecture and then develop their own silicon, potentially based on their own implementation of the architecture. This enables a lot of innovation, but it also risks leading to fragmentation. UEFI is functioned as part of the solution for how to reduce that fragmentation. Various companion specifications describe how to create systems that can be supported by UEFI. By following those specifications, OEMs can create systems that will work like customers expect. By following UEFI strictly, others can create drivers and applications that will work across these different systems. Linaro helps to enable the ecosystem by giving a natural place for ARM licensees, who are competitors, to work together for mutual benefit to solve common problems. One of the things I tend to complain when people start getting too innovative is that, and they claim they're doing differentiation, is sometimes I'd go, are you sure you're not just trying to be different? On its own, the ARM architecture doesn't contain enough defined behavior to enable off-the-shelf operating systems to run. On the data center side, we have two companion specifications that help people actually build systems that can run firmware that, if implemented according to the firmware specification, can look like a coherent platform that you can just run a generic operating system installer on and install all generic stuff. We currently have efforts underway to do the same for the embedded segment via the introduction of an embedded baseboard requirements document, EBBR. So what are practical differences then between ARM and PC? Going on a slight tangent, a few years ago, Art Bischovel here and Alex Graf at SUSE sat down and put together a solution to execute x64 option ROMs on AR64 via emulation. This was basically a follow-on on our campaign to revive EBC, having failed spectacularly. So we needed a way to get people a shorter time to actually start being able to use existing PCIe cards would not already have AR64 drivers. But the problem with emulating is that you need to mimic bugs as well as correct behavior if you're actually going to be compatible. So one thing that we found was that the option ROM emulation turned up some common issues when testing existing drivers compiled for x64 on AR64. I think the most common by far is, well, certainly the one we hit most frequently, is failure to check for null pointers, meaning that because on PC, remember, there's always RAM near address 0. If you dereference a null pointer, there's going to be something there. If you overwrite it, well, maybe it wasn't that important, you won't notice. The second one, I said, on ARM systems, you may not have any RAM, so it just won't work. Assumptions, the second one was assumptions that DMA or other buffers need to be located below 4 GB. So something tries to allocate a DMA buffer and it gets given a DMA buffer and it goes, oh, but that's above 4 GB, so I can't use it. That's a bit of a shame. And the third one, and really also very common, is the failure to use the proper UEFI interfaces for PCI and DMA. And Art will get into a bit more detail on the specifics of what that means. But the fundamental point is that none of the above would trigger an error on a PC platform. All of these are errors in existing option ROMs that were certainly in the market then, and several of them probably still are. Art.
Yeah, so this is basically the reason I'm here, to test PCI third-party drivers on ARM systems. Basically, the PCI spec is much more permissive in how you organize the topology compared to what we actually see in PCs. So in PCs, everything is identity mapped, everything is coherent, everything just looks very boring. But what you actually can do, and what we see in ARM systems, is where like bar accesses are actually a different. So the bars are in a PCI address space which is not mapped, identity mapped on the CPU side. DMA that's not mapped, it's not identity mapped, so the inbound translation. Another thing we have to deal with is non-cache coherent DMA, so that's not actually a thing we care about on servers or more high-end systems, but well, since the spec, well, the PCI permits it, the UEFI permits it, only the drivers can't deal with it, so that's another thing we identify as an issue. Yeah, there are a couple of other issues. I'll have an example later, what it looks like. So this is typical for PC, and it's actually what we prefer to see on all the systems because it's just the most trouble-free way of putting things together. So there are two different, there's the PCI address space and there's the host address space, but they're just identity mapped. So all the arrows going left and right, they just use the same address space, and also peer-to-peer accesses between devices are all in the same address space, and there's no translation or anything. However, well, this is one of the examples we actually see, and this is not a server chip, but a high-end 64-bit ARM chip, where there are actually several host bridges, and every host bridge just has a single root port, or actually it doesn't even have a root port, it's just a PCIe link. And in this case, well, all the different arrows may actually involve some kind of translation. And especially if you want to do peer-to-peer in a configuration like this, it's really very painful. But it's the spec permits it, the PCI spec permits it, the UEFI spec permits it, so the drivers that we validate should be able to deal with crazy topologies like this one. So the UEFI spec is actually pretty portable. So from the API level, everything we need to support those topologies and configurations is actually there. The problem is that, well, you can get away with not using them at all and just go around it. And such drivers, so all the drivers we have in the upstream, like in EDK2, all the class drivers for NVMe and USB and SATA, they are all fine. They're all clean and you can use anything you throw at them. But many of the drivers that I see here have problems. So this is like a standard example of what you should be doing. So for a USB host controller, the like rings in memory, or for a network card, the data structures that are shared between the DMA master and the CPU. You actually have to use the PCIe protocol to allocate that buffer in the first place. You can't just grab some memory and map it. You have to use the API for that. And then when you do that, you have to map it. So first you allocate, then you map it. And the mapped address that gets returned from the map call is what you give to the hardware. So that may be different from the host address that your CPU actually uses to access the same memory, because there may be translation involved. Yeah, so the size of the map could deviate. That's not actually something you often see in practice, but it's another thing you should have to check. But the most important part is that, well, you map in the first place, and if you do map, then you use the device address, not the host address, to pass into the device. However, in practice, if you do this on a PC, it just works. So you do some allocation and you get a CPU host address, and that's the host address you use for the CPU, and it's just the same address you just poke into the DMA registers. And because everything is one-to-one mapped and everything is coherent, you don't actually notice that there's anything wrong. Note that even on a PC, this breaks when there's any kind of IMMU involved, because then you can't actually do this. But, well, apparently in practice, those are not widely used in the firmware because, well, many drivers don't bother doing this. This is another example I found recently. So, anyone care to venture a guess what the intent of this code is? It's only 3 lines, so it shouldn't be too difficult. I'm sure someone knows. Oh, yeah, please.
Pretty clear that your first line is intended to determine the size of the buffer you need to allocate in order to hold a string that you're printing. And so it's just like, let's spit this string out to some arbitrary location that we don't care about. No! Oh, sounds good.
Yeah, basically, so that's basically what it does. So the assumption on the part of the program is that passing a null buffer and 0 buffer size actually gives you the behavior that it only counts the characters without doing anything. But in reality, it actually prints the string to address 0, which apparently worked on PCs. On ARM, this fails spectacularly unless you happen to have memory there. Otherwise, it just crashes very hard.
I would never do that even on a PC. That's hideous.
Well, it is hideous, but if the API actually has that behavior, then it's fine. If this is actually how sprint is documented as operating in practice, it just turned out not to be the case. But yeah, nobody ever noticed because it happened to work, and that you're actually writing to address 0 in the firmware, that's, yeah, well. To be fair, I don't think shim typically prints anything at all if it runs normally. So this is like in an error logging path, but yeah. Yeah, so the other problem that Leif already highlighted with this is that if you typically have some address below the 4 gigabyte mark, it means you don't have to care about 64-bit DMA. So in the EFI PCIe protocol, when you enable a device for DMA, you have to actually set an additional attribute if it's 64-bit DMA capable. And if you don't do that, then the bus driver infrastructure will not permit DMA to an address above 4 gigabytes. So lots of drivers never bother to set that because on a PC you don't need it. I mean, when you're running in UEFI, you have plenty of memory to do DMA anyway, so why would you care about 64-bit DMA? But on an ARM system, there's maybe not any memory to begin with, and then DMA is just broken and you can't use the device at all. And actually most PC firmwares that I've interacted with don't appear to enable 64-bit DMA in the first place. So even if the device is capable, the host bridge driver doesn't actually enable that capability because, again, it's not really necessary. Yeah, so typically for a portable driver, you should assume that if your device supports it, then you should just enable 64-bit DMA in your driver, and if it's not used, then it's not used. But if it's necessary, then at least you will have the ability to use it. And I'm pretty sure PCIe mandates it, except maybe for legacy endpoints. But so there's really no reason to not enable this. Well, cache coherency is another problem. So if a platform has non-cache coherent DMA for PCI, then all the cache maintenance and all the tricks you have to do to actually make this work, they're all abstracted and, well, they're put into the host bridge and bus drivers. And if you just use the APIs, the driver really doesn't have to care about any of this, and it will just work. And it's, well, this is another kind of, so last time with the Plugfest in Taipei, I brought a system that was actually non-cache coherent for PCI, and then you, well, see drivers breaking as well for this reason. Again, sorry.
Another thing that's relevant to know if you're moving to specifically porting drivers to ARM, which may not actually be applicable if you're doing specifically PCIe OpenROM development, because as long as you use the proper interfaces, again, they will handle this for you. But another strong difference between ARM and PC is that the PC is basically a strongly ordered memory model. It might arguably not be as true as it once were, but it's certainly a lot more strongly ordered memory model than ARM has. But I mean, UEFI is mostly a single-threaded execution environment. In some firmware implementations use the PIMP protocol, which should also be fine because then you have explicit synchronization mechanisms provided. But the ARM architecture only guarantees the ordering of memory accesses in regions marked as device and strongly ordered, and even there it only guarantees it within the same 1 kilobyte region. So if you have any driver that, or test application that has a specific requirement on writing two or making two transactions in a specific order, you do need to use the memory fence macro to make sure that they happen in exactly that order. One example is updating a DMA descriptor and then initiating a DMA transaction, and the other is a sort of write, delay, poll thing. Yeah, and just repeating that afterward. And so we come sort of to the benefits of testing on other platforms. As Ard mentioned, he put together a worst-case system, which we nicknamed Chucky, for triggering the most common issues in drivers. He brought it first to Taipei, and it was a big success there, so we have it here again. The system has two separate PCIe host bridges and several selectable behaviors which can be set by dip switches. So if you have drivers that are broken on one specific thing, then we can stop trapping on that and then see if it passes the other things. So it can mess about with the MMIO translation between the host bridges. It can make sure that there is no DRAM below 4 gigabytes, which means you get no 32-bit DMA. You get inbound translations for the 32-bit DMA on host bridge B. Ard, bus enable a bit.
Yeah, so what I did was remove the code that when you enable the device and you enable memory and I/O decoding, not to enable bus mastering at that time, but defer that to the first map call. So if you don't bother to call map on map in the first place, then your driver will break. And well, that actually caused some issues. So yeah, people are clearly not doing well.
So it just won't work. And of course, having no DRAM near 0 means we catch the null pointer references. And finally, sort of cross-architecture toolchains. In the past, we've kind of suffered a bit from the fact that most people doing firmware development for ARM have been using GCC or Clang, whereas most people doing development for PC have used Visual Studio. But we now have, I mentioned here, Visual Studio 2017 15.4. There was a preview release. That was the first one that included kind of all the bits you needed in order to build drivers or platform ports for AArch64. But I think it's in 15.8 or whichever was released sometime October, November. There's actually now full official support for AArch64 in Visual Studio. So if toolchain issues have kept you from trying to build your drivers for ARM before, that's no longer a good excuse. A few final notes. It's completely possible to write a device driver application that can be easily compiled for either x64 or AArch64 and just work. It's also very much possible to write a driver that works on x64 and not on AArch64, but that is usually due to bugs in the software. And fixing those bugs might actually find issues that you would otherwise trip over at some point in the future in the field, even on x64. So writing drivers portably increases code correctness and reliability, and testing on multiple architectures catches even more. Right, so that's it. Any questions?
Are there any like simulators or test harnesses or other things that people could use to try a driver on an x64 system but verify that it's behaving in a way that would work on an ARM system as well? Or else an ARM simulator that has enough detail to pick up these problems?
Well, I guess for the, especially for the PCI stuff, having like a recent x64 system that has the VTD IMMU pieces enabled in the firmware would actually trip over in the same way. Because if you don't, well, the translation maybe is different, and that's actually something we discussed with the Intel guys the other day. So even if you have the OMU, there probably won't be any translation. It just, so the MMU doesn't map anything, and if you map something for DMA, it will actually open a hole in the IOMMU mapping. We should probably add some translation there just to weed out the offenders, basically, because that would be trivial.
So ACPI spec supports describing translation offsets, right? So it can't be unique to ARM, right? It must have existed before.
I mean, PCI supports it. So
Right, and the ACPI spec supports it, and it wouldn't have gone in the ACPI spec unless there was a system that already had that problem, I imagine.
the point is that
We used to have we used to build a titanium system.
There you go.
Same issues.
Okay.
yeah, so the point is, PC systems are quite uniform, and most things that aren't PC systems are less uniform.
I was just curious because I've seen it.
Yeah, I think when we started to enable that stuff in Linux, like having the type translation in the resource windows in ACPI, that was actually giving some problems. So it's there in the spec, but the OS didn't actually implement it correctly. So.
Okay, thank you.
There's one more.
So just to double check, you had mentioned about the approach to emulate execution of x64 drivers on ARM. Is that still the main approach that is being used, or was that just something that you tried and abandoned?
I would say it was never intended to be used. It was always more of a, we want to test this card right now in this machine. Can we do that? Especially with things like, maybe I shouldn't point segments out, but there are some cards that have device drivers in Linux later on that expect that certain configurations have been done by an option ROM in order for the device driver in the operating system to run properly. So in order to be able to get those to run, if you have the emulation, then that works. And also just as a quick and dirty fix to be able to get some, so you can actually get a graphical console in UEFI. So it was never meant to be a solution, it was meant to be a sort of vehicle to move it forwards and then maybe talk to people saying, look, we have these people who want to use your card, would you consider building a native driver for them so we could do that? Possibly also going, and by the way, you seem to be doing some null pointer dereferencing, you might want to look at that. Okay, thank you. By the way,
Thanks.